Hi, everyone. My name is Abigail Bodner. Thank you for anyone who's decided to join and listen to this talk. I'm going to be introducing recent work with Laura Zana and Andrew Ross at NYU on a machine learning approach for relating coastal sea level to its local drivers. So on a global scale, we have a fairly good understanding of what's going on. We're able to measure over several decades of satellite imagery already, the globally average sea level, and study how it's rising primarily due to glacial melt and thermal expansion. However, on a regional scale, we have a much more complex picture. The local relative sea level is going to depend on atmospheric forcing. It's going to depend on water properties such as density, the circulation of that region, the bottom bathymetry. So all of these different properties are going to determine the effective sea level, which you can see varies up to even a meter for different regions around the globe. And how much it varies is going to determine really the fate of coastal communities that rely on sea level predictions to better prepare for future climate change. However, regional sea level is a multi-scale problem, and it's determined by a wide range of spatial temporal scales, from the global scale to what's really going on local scale, as well as the different forcings that we've discussed. And the current observations that we have tend to be sparse. They could be noisy, whether it's tide gauges or altimetry data that becomes less robust as we get closer to the coast. The model simulations that we have do not necessarily resolve all processes that are important on the relevant scales for sea level. So today we are going to discuss a new approach, which is a data-driven approach to try to understand the physical drivers of coastal sea level. And we're doing so by making use of model simulations and observational measurements. I'm going to focus today mostly on model simulations and then discuss how this ties in with observational measurements in the future. So the method that we're using is a machine learning convolutional neural network, which essentially pairs between the input, which are physical drivers that are related to sea level, and the output is the coastal sea level that is the effective sea level signal at the coast. And the network learns this relationship between these two, where it studies the patterns in the physical driver's inputs and relates it to what would be the signal at the end. This is known as a deep network for regression. And it updates the weights of the network at every iteration until it reaches an optimal relationship, which then could get used to make predictions based on a certain input, what would be the effective coastal sea level we would expect. So today, as I mentioned, I'm going to be primarily using results from simulated data, and we're focusing for now on the North Atlantic region. We're looking at 15 years of MOM6, CM2.6 pre-industrial control. So this is a 1/10 of a degree model simulation, and we've got daily data, and this is a pre-industrial control, so it means that we don't vary the atmospheric, the CO2 forcing. So we're using this primarily to understand the physical relationships. We've identified some open ocean properties that are relevant for coastal sea level. Obviously, these aren't all of them, but we've chosen these to correspond with observational measurements that exist in the real world, which I'll touch on in the end. So we're looking at sea surface height, sea surface temperature, sea surface salinity, sea level pressure, bathymetry, and ocean interior stratification in the form of M², which is the Brunt-Weiss solid frequency. And all of these have been shown in many other studies to be related to sea level. And we're using these as the inputs to then tell us what should be the coastal sea level that we should expect based on these properties. So just to get a sense a little bit of what these might look like in the network, we have to work on the data a little bit before we let the machine learning method learn it. So we calculate the anomalies, we normalize the data to unit standard deviation. And we also found that there's a very high correlation between what's happening at the coast and other properties along the shelf. So what we've done is we've actually masked the entire shelf and further separating the open ocean with the signal along the coast. This is also somewhat what happens with satellite altimetry as it becomes less robust as we get closer to the coast. So we now have open ocean sea surface height, and we've got the coastal sea surface height that we're trying to predict based on these patterns. We do the same for the rest of the other input variables, so sea surface temperature, salinity, sea level pressure, bathymetry, and n squared averaged over the upper ocean. Now, as I mentioned, we have 15 years, so these are 6,000 days. We'd like to train the network on the widest range of possibilities, so we'll be able to generalize well. So we randomly split this data set into a training set, a validation set, and a test set, where the largest portion gets used to train the network so it gains knowledge on the different possibilities. We also retain some for the validation set, which is used to tune certain hyperparameters, like, for instance, how many iterations we have to go for. And then 10% gets saved for testing the method in the end. So the model the network never uses this data in order to learn from it, but it gets used to see how well can it generalize. So all of these input variables are being used as in the input layer, which then follows through to predict the coastal sea level. It calculates the error, how well did it do, and then it goes back, adjusts these weights, and tries again until it reaches an optimal prediction. So what does these results look like? So I'm going to show you some results for the training process. So remember, this is as the network is learning, it's updating itself to minimize the error on the data. So we would expect these results to be quite well, because this is how the network is learning to predict. So here is a result of what the sea surface height would look like at a single coastal location. Blue is truth and orange is the prediction, and you can see that it aligns fairly nicely. This is the distribution of that same location. So we can see also that the truth and prediction are for the most part aligned. Another way to understand the results is we can look at the correlation between the truth and the prediction. So if the true sea surface height is very high, is the prediction that same value? And along all these coastal locations that we've looked at, we can see we have a fairly perfect correlation, which again is not surprising, because this is how the network is learning. It's learning to make that prediction well. We can also look at the mean square error, which is the size of these circles. So the larger the error, the larger the circle, the smaller the error, the smaller the circle. And this varies depending on the location, which also indicates something about the physics of that region, which I'll talk on in a bit. But for instance, around here in the southern region, we've got a fairly low mean square error. And then around the estuary in the Delaware Bay, we get a larger error, which might hint that there are other physical drivers that we aren't accounting for, or perhaps other types of dynamics are dominating the bay. These are the results on the unseen data. So this is for the test set. And at first glance, it doesn't do as well as the training. So perhaps this is something we might work on to even tune the model even further to make sure we are able to generalize better. For the most part, we can see that some extremes don't get calculated as well. Also, the distributions change a little bit. So this is something we're looking into to understand, also especially how it relates to capturing extreme events. However, we do see the correlation is fairly high, even for the train set. It's above 0.8 for all. So the mean square error is what we're going to be looking to improve, especially again in this Bay Area, where it seems to be larger. We are now looking at several different angles to try to better understand the method, to try to better understand the physics of the domain. So one thing we can look at is the different seasons. How do these results vary by season? So for example, in the springtime, in the summer, we don't do as well in this Bay Area again. So perhaps this is hinting at like glacial ice melt or river runoff that is not an open ocean driver, but it does affect the sea level of that location. We're also looking to see what happens if we remove one of the input variables. Are they all necessary? How does the network perform? So for instance, here we remove sea surface height, remove sea surface temperature, and so on. And one thing that's worth pointing out is if we move sea level pressure, especially in this northern region, the results decrease. So atmospheric dynamics might be a very important part of that region. So again, this is already hinting at the physics of the location. We can also look into using only one variable at a time to see if that's good enough to make a prediction, or how well is it. So for instance, in sea surface height alone, which may not be so surprising, we do a fairly good job of being able to predict the sea level at the coast. Again, this is the same variable in the model, but it won't be in the observations. But there are locations where it's not as good. So perhaps, there's another variable that might be enough to reach good results. Again, this is hinting at the dominant physical properties of this location. Bathymetry alone is not enough to predict things on the timescales that we're looking at, because of course bathymetry doesn't vary on daily timescales. But it turns out that the error is smaller when we include bathymetry, so it may act more as an amplifier than as a driver. So all of these different angles are things that we are currently looking at to understand. And to summarize the current results, we're looking at a supervised machine learning method to predict coastal sea level given certain open ocean properties. We've identified 6 different properties for now, which are used as inputs to predict the coastal sea level. We are focusing for now on the North Atlantic, and preliminary testing has shown that we have high correlation between the truth and what the model will predict. So this is giving us confidence that by fine-tuning certain hyperparameters and perhaps including more data, we'd be able to reach an even higher prediction on data that is unseen. And the prediction error seems to vary by location, season, and dependent on open ocean properties. So all of these are related to the physics of the problem as well. And these are angles that we're looking at to better understand. As I mentioned, we'd like to adapt this to include observations. So the input variables that we've looked at before are actually correspond to observational measurements we have in the real life. So from satellites, we have bathymetry, temperature, salinity, altimetry, sea surface pressure. From ocean drifters, we've got information on the interior for stratification. From tide gauges, we've got coastal sea level. So this is the mean sea level trend in Honolulu, where we're all supposed to be. And we'd like to utilize this information to really constrain our method with what's happening in the real world, not what's only happening in the model. So to do so, we're going to use a transfer learning approach, which means that we train our network on the simulated model data and then transfer that knowledge or transfer the network to then be used on observations. And this is a tool that's been used already in several scenarios, also in the environmental sciences world, and it's been shown to be pretty powerful in making use of sparse and noisy observations by first founding the information with abundant model data. We will then turn to really interpret and explain what's happening in this method. What are the physical relationships that exist between the drivers and the effective sea level, and how can our method explain them? So to summarize, we're looking at a data-driven approach to understand physical drivers of coastal sea level. We have preliminary results and sensitivity tests that we've used on simulated data, but we plan to, in the next step, use a transfer learning approach to include observations. And we are interested in understanding which physical drivers are more important, why, when, and where. And we are expecting to expand to regions beyond the North Atlantic and explore future climate scenarios to see how the statistics change and how our results compare with current predictions. Please let me know if you'd like to chat, and I look forward to meeting everyone in the discussion session in a few weeks.